Welcome to part D of this unit. In the previous part, we went through the calculations using our case study of an X-bar or mean chart and also a range chart. As a reminder that if my measurement data that I am collecting is variable data, then the control charts that I will use will be the X-bar, the mean, and the range chart. Now we'll talk about the other type of data that we could have in statistical process control, and we'll take a look at the case study on it. So the other type of data that we can have besides variable data is referred to as attribute data. So attribute data is a type of measurement where the data can take on only certain values. It cannot take on any value, just only certain values. And there are two types of attribute data. There's one type of attribute data where the values that you measure is binary. That is, it is either good or bad. So an example of attribute data that is binary is if I am doing a measurement of a process for an assembly line producing cell phones, and I'm going to be doing a quick test of cell phones coming off of this assembly line. I'm going to pull some samples, and the test that I'm going to do is connect them to a power supply and hit the on button, and if it turns on, then the cell phone is good, but if the cell phone does not turn on, then it is bad. So for each phone, the measurement, there's only two conditions. It's either good or it's bad. That is an example of this type 1 of attribute data. The other type of attribute data is when we have a process where there could be several potential things that could go wrong with it. In other words, there could be several different types of defects. And what I'm going to be doing is I'm going to be measuring, and I'm just going to be counting the number of different types of defects that I find. So an example of this would be for an automobile assembly process. So automobiles coming off the assembly line, there could be several things that could be not quite correct on each car. So one car, I inspect it and I count how many things are not quite correct on it, and there were 6 different types of defects there. And on another car, there was only 5 types of defects. There could be some cars that don't have 0 defects. So this type 2, what I'm doing is I'm counting how many defects that I find. Where type 1, it's binary. It's either good or bad. So if the data, the measurement that I am collecting for a particular process is binary data, good or bad, the control chart that is used for that type of measurement is referred to as a P chart. If, however, I am using the second type where I'm counting the defects, like counting the number of defects in an automobile that has just been assembled, then I'm going to be using a C chart. And in this part, we'll be going through the case study for a P chart. So P stands for percent defective. Percent defective. So as an example, going back to my cell phone example, I tested some cell phones. I put power to them, turned them on, and I pulled a sample of 100 cell phones to test. There were only 5 that did not turn on, which means that there were 5 that were bad, which means there were 95 that were good. So out of that sample of 100, 5 divided by 100, or 5%, were defective. So in our process, if this is a process we've been doing for a long time, we may know historically what percentage of our production is defective. But if we do not know what the little p is for a process, because perhaps it's a new process, such as my steak restaurant, and we just don't know what the percentage of defective steaks will be, then we have a formula for estimating what the percentage defect would be. And the formula is shown in this slide. We call this P bar. So this is an estimate for P, and the formula is the total number of defects divided by the total number of observations. Now, we have a formula. We have another variable in the P chart, which is shown here. This is called sigma sub P. So again, P is the percent defective. So P bar is an estimate of the percent defective. We're assuming that we have a normal distribution curve, so there should be some standard deviation around that percent defective. And the formula for calculating what the standard deviation is around the percent defective is shown in this slide here. So it's P bar, the square root of P bar times 1 minus P bar divided by little n. And again, little n is the same variable we've been talking about before. It is the sample size. It is the number of observations in each sample. So let's apply this to our case study of Deluxe Super Steakhouse. So we have some data that we've collected. So what we're using here is the criteria if a customer is displeased with the way that their steak is cooked. They always have the option of sending the steak back to the kitchen and having another steak cooked to their satisfaction. So when a steak is brought out to a customer, there's only two possible things that could happen. They're pleased with the way that it was cooked, which means it's good, or they return it to the kitchen, which means it is bad. So this is an example of a binary condition. The steak is either good or bad. So we took data over 5 consecutive days. So on Monday, out of 50 steaks that were cooked, 6 were returned. That is, 6 were bad, the rest were good. On Tuesday, 50 out of a sample of 50, 3 were returned. On Wednesday, only 1 was returned. Thursday, 4 were returned. And Friday, there were 7 that were returned. Okay, so what is the value of little n? What is the number of observations in each sample? Well, the answer is 50. There were 50 observations in each sample. Okay, what is the percent defective each day? Well, we're going to calculate that. And what is P bar? Well, we're going to calculate that. And then we're going to create a 3 sigma control chart and determine if the process is in control. So a 3 sigma control chart is going to indicate then our formula for the variable z, as in zebra, we will substitute the number 3 for it. So we first need to calculate what the percent defective is for each day of the week. So on Monday, there were 6 defective out of a sample of 50. That's a 12% defective rate. Tuesday, it was 6%. Wednesday went down to 2%. Thursday went up to 8%. Friday got a little high on Friday, went up to 14%. So we saw that there was variability in the process, just as we expected there would be variability. The question that we don't know yet, is this variability the result of randomness, or is it the result of non-randomness? So we know what P is, and now that we know what P is, we can calculate what P bar is. So P bar is the ratio of the total defects divided by the total observations. So if I add up all the defective stakes for the entire week, I get 21. And then the total number of observations over that same time period, there were 50 stakes that were observed each day over 5 days. So there were a total of 250 observations in that week. So P bar is 8.4%. Now that I have P bar, I can calculate what the standard deviation is for P. So 8.4% as a decimal is 0.084. That's where we get the 0.084 in the formula below. So the formula was P bar times 1 minus P bar divided by the little n, and the answer to this is 0.04, is the standard deviation. So now that I know P bar and sigma sub P, I can calculate the control limits. So P bar is 0.084, sigma sub P is 0.04, and my Z value will be 3 because the problems asked for a 3 sigma control chart. So the upper control limit is going to be 0.2 or 20% defective. The lower control limit, the calculated value is negative 0.033. Now students, for P charts, and then we'll also see this again for the C charts, if the lower control limit calculates to be a negative number, that is an infeasibility. So let's remember what we're trying to do here. A P chart is the percent defective. Is it possible to have a percentage defective that is a negative number? That's infeasible to have a negative percent defective. So if the lower control limit is a negative number, we're going to round up and we're going to make it the lowest feasible number that we could have, which is 0%, 0 defective. So now I have my control limits for my P chart, 20% and 0%. I can draw my control chart. So I have my 20% upper limit and lower limit, and I'm going to plot my data for each day of the week. Now, again, what data am I going to plot? So for the X bar chart, the data that I plotted was X bar data. For the range chart, the data that I plotted was range data. Now I'm at a P chart. The data that I'm going to plot here is going to be the P data. So on Monday, the percent defective was 12%, and for Tuesday it was 6%. So that is the data that I'm going to plot. Now I'm going to observe if all the data points fall between the upper and the lower control limit, which they do, and I'm going to conclude that this variability in this process is the result of randomness, and therefore the process is in control. This concludes part D of this lecture. Please continue to the next part.